So as you can see here, we're going to use our trigonometric substitution. Since we have x squared minus 1 here, it could be easily substituted with a sec theta, since x squared minus a squared is similar with x squared minus 1, 1 being our a. So here we have our x value. Since we have our x squared there, we're going to raise it by 2, and leaving us with secant squared theta. And for the x cube value, we have secant cube theta. And to derive our x, we have secant theta tan theta d theta. So here, to get our theta, it's going to be equal to arc secant x. And for our Pythagorean triangle, we have secant theta equals to x over a, x being our hypotenuse and a being our adjacent. And we have square root of x squared plus a squared as our opposite. Here we substitute our values, giving us with square root of secant squared theta minus 1 over secant cube theta times the derivative of x, which is secant theta tan theta d theta. Here we could cancel out our like terms, secant cube theta and secant theta, and replace this with our trigonometric identity, which is tan squared theta over secant squared theta, since we canceled this out already, times tan theta d theta. In this equation, we could actually eliminate our square root, giving us with tan theta times tan theta over secant squared theta d theta. Here we could multiply this both and have this equation. Integral of tan squared theta over secant squared theta d theta. And in this part, we are going to use our trigonometric identity. For tan squared theta, we know it is equal to sine squared theta over cosine theta. And for secant squared theta, it is equal to 1 cosine squared theta. Putting it into this new equation. Now, we're going to make it in a simpler way using our fraction rule. So here, using our fraction rule, we came up with this, the reciprocal of 1 over cosine squared theta. So we could easily cross-multiply them and cancel out our common terms, leaving us with integral of sine squared theta d theta. Now we're going to use again our trigonometric identity, since we know sine squared theta is equal to 1 minus cosine 2 theta over 2 d theta. Now it's so much easier to integrate, and now we're going to let out our constant, which is 1/2 integral, leaving us with 1 minus cosine 2 theta d theta. Now we could distribute our integrals. Since the integral of d theta is theta, and the integral of cosine 2 theta is 1/2 sine 2 theta, we're going to distribute our 1/2. Now, and again, we're going to use our identity for sine 2 theta. Since we know that sine 2 theta is equal to 2 sine theta cosine theta times 2 sine theta cosine theta, leaving us with a new equation. Oops, this is 1/4. Since 1/2 times negative 1/2 is negative 1/4. My mistake, I'm sorry. So there, 1/4 times 2 is 1/2. Here. Now we have this new equation. And since we use our trigonometric substitution in the first part of our solution, we're going to use it now too. Since we have sine theta, cos theta, we're going to get their values. So since sine theta is equal to opposite over adjacent, hypotenuse rather, and cosine theta is equal to adjacent over hypotenuse, we could simply use our triangle that we made earlier and substitute their values. Opposite is square root of x squared plus a squared over hypotenuse, which is x. And for the cosine theta, we have adjacent, which is the a, or 1, over hypotenuse, the x. Now we could simply substitute the values. 1/2, for the value of theta, we have arc secant x. And now, for the value of sine theta, we have square root of x squared plus a squared. A is equal to 1 over x times 1 over x plus c. Now we could simplify this equation. X squared plus 1 over 2x squared plus c. That's our final answer.